Okay, hi guys, so here's G-1, take two for me. I kind of messed up. Okay, so I'm going to do 3 examples from the practice. They're all even ones. So it says here, I wrote find the indicated derivative in terms of x and y, but I want to say instead in terms of the variables in the original equation, because they're not always x and y in this for this phase. Okay, so let me just introduce some notation real quick. So let's say that we have an original, I don't know, function or term or something called, let's say it's y. In prime notation, its first derivative is y prime. But here's the thing, guys. There's something called a second derivative, which is the derivative of the first derivative. And it doesn't give you the information, like the first derivative gives you the slope of the tangent line to the original graph. The second derivative does not give you the slope of the tangent line to the original graph. It gives you something different. If you were to graph the derivative function, which is a thing, we're going to do that soon. If you were to graph the original, or if you were to graph the derivative function, then you could think of the second derivative as like the slope of the tangent line to the derivative graph. But it's not, it gives you different information than the first derivative about the original function. And we'll talk more about that, I think, next cycle. Okay, but the second derivative is y double prime. It's the derivative of the first derivative. But guys, this is prime notation, which is super simple. Leibniz notation is a little more complicated. Let's just say, let's just say y is equal to y of x. All right, let's just say that. Then, so let's just say our original is y. So if y was equal to y of x, Leibniz notation would say dy over dx for the first derivative. And for the second derivative, this might be a little bit weird, but it goes like this. It goes d squared y over dx. That's what it looks like. All right. And, okay, so here is this. So for number 2, they're asking us to find, d squared y over dx squared. And so this, what this means is they're asking us to find y double prime. And let's just make a note. So remember, they are implying here, by asking us to find this, they are implying that y equals y of x. So that means that we're going to need a y prime after a y derivative, all right? Because that's where the chain rule would be happening. All right, let's do it. So the derivative of 5x is 5. Derivative of 3y squared is 6y, y prime, because of this. Derivative of 1 is 0. It's a very common mistake, guys, that people will just bring down the constant and forget to take the derivative of it. But so just be aware of that. Okay, so that is the first step in finding this. The second step is solving for y prime. So we get y prime is negative 5 over 6y. That's the second step. The third step is to take the derivative again. But before taking the derivative, we should ask ourselves, so when we take the derivative of this, we're going to have y double prime, because it's the derivative of the first derivative, which is the second derivative. But on this side, you should think ahead. What rule am I going to use? And if you can find a way to write this like this, then we can use the power rule. You might see a fraction and say, oh, I'm going to use quotient rule, but it's good to avoid quotient rule when you can, because it's a pretty lengthy process. And if you can get it to look like this, then the derivative is just a(ny) to the n minus 1. In this case, we would need a y prime at the end. So actually, we can write it like that. If you just raise the y to the negative 1, so this is y prime equals negative 5/6 y to the negative 1. Now, I know that this, and somebody was mentioning this to me earlier, this does look like y to the first, but we just have to understand from the context, the larger context of the problem, that it means y prime. And your reader would totally know that. Okay, now keeping in mind, we're going to take the derivative, and we, again, need a y prime after a y derivative. All right, so this is going to be y double prime equals 5/6 y to the negative 2, and then y prime after a y derivative. Now, here is the thing. They want us to find the indicated derivative in terms of the variables in the original equation. So look at this original equation. What are the variables in it? X and y. So we've got y double prime here. So this is our answer, but it is not in terms of x and y. It is in terms right now of y and y prime. So what we want to do next is we want to leave a blank for the y prime. All right, I'm leaving a blank where the y prime was. And guys, we actually already found y prime in this step here. So you're going to replace the y prime in the second derivative with your y prime answer from when you did the first derivative. So negative 5/6y. And you don't have to simplify at all. So that is the answer right there. Now, this next one. Okay, I can do 2 more. If you feel like you've got it, you don't need to see any more, that's totally up to you guys. Okay, but I'm going to do 2 more. I'll show you. I'm going to do number 4, which is this one, and then I'm going to do number 6, which looks like this. All right, so I'll go a little bit faster. So here, what does this mean? This is actually different than the first one because now the x is on top. So guys, this means that they want x double prime. They want x double prime. And we're going to need an x prime after an x derivative. Okay, so now we're going to take the derivative. So the derivative of y squared is 2y. You don't need a y prime because they're asking for, because of this, what I wrote down here. Plus, this is 8x, x prime equals derivative of 1 is 0. Then you solve for the first derivative, which is x prime. Negative 2y over 8x. All right, and guys, if you can, if you notice an opportunity to reduce some fractions or something, that's probably a good idea because, it just makes any numbers you're working with smaller, but you don't have to. Okay. Now, here, we're going to take the derivative again. This is not a situation where I can rewrite like this because I've got both variables involved here. I've got of the y and the x. So we need to use quotient rule. We have no other choice. So I'm going to use quotient rule now. And as I'm using quotient rule, I'm really going to concentrate and remember that I need an x prime after an x derivative. I don't need a y prime after the y. So taking the second derivative. So x double prime equals the derivative of negative y is negative 1. Bring down the 4x minus, bring down the negative y. The derivative of 4x is 4, but we need an x prime after an x derivative. And this is all over 4x squared. Okay. Now I'm going to clean this up a little bit, but remember they want this in terms of the variables in the original equation. Here's the original equation. My variables are x and y. So I just want x's and y's here. I don't want this x prime. And this is the part where you remember that x prime is negative 2y over 8x. So you can replace x prime with that. So let me clean this up just a little bit first. So x double prime is negative 4x plus, I'll say 4y all over 4x squared. So I left a blank where the x prime would go. And then in for that, I'm going to put negative 2y over 8x. Oh, you could have put this also. Yeah. Okay, that's fine though. Okay, now if you want to stick around, I'm going to do this one, but you don't have to stick around. All right, so here, this means g double prime. So I'm going to need a g prime after a g derivative. So 0 equals 12 f squared minus 8 g prime. I'm going to solve for g prime. This ends up being 12 f squared over 8g, right? Because it'd be a negative over a negative. Okay, and now just so my numbers are a little bit smaller, dividing by 4, so that's 3f squared over 2g. Now I will use the quotient rule for the second derivative. So 6f 2g minus squared 2g prime all over 2g squared. Okay, and now I'm going to clean this up a little bit and then substitute g prime back in. So this is 12 fg minus 6 f squared. Okay, so this is where g prime would be, and I'm going to put this in instead.